Last video, we talked about the left-hand side of Gauss's law. In this video, we're going to be talking about the right-hand side of Gauss's law. And more specifically, we're going to be talking about different materials that we're going to be using when applying Gauss's law. So first, we're going to lay out what we mean when we're talking about the right-hand side of Gauss's law. Then we're going to talk about conductors. And then afterwards, we're going to talk about insulators. So to remind you of Gauss's law, and specifically the right-hand side of Gauss's law says the integral over the closed surface of E dot ds is going to be equal to Qn divided by epsilon naught. And really what we're going to be doing is focusing on this Qn, which is the charge that is contained within the closed surface, and more specifically, the total charge that is contained within the closed surface that we're forming on the left-hand side of Gauss's law. So let's look at conductors. So when we're talking about conductors, there are three principles that we want to keep in mind. The first is that charges can move. The second is that charges are only on surfaces. And this is kind of a consequence of the fact that charges can move. So charges are going to move away from each other. When we're talking about electrons, they repel each other. And so that means that they're going to try to get as far away from each other as they can, which means they're only going to reside on surfaces. The final thing that we can say about conductors is on the inside of a conductor in electrostatics, the electric field is going to be equal to 0. So in order to think about this, let's consider some spherical conducting shell that has some inner radius of A and some outer radius of B. So now let's put a charge of plus Q at the center. And ultimately what we'd like to do is determine what the charges are on the inner surface A and the outer surface B. So let's consider Gauss's law again and draw some Gaussian surface. So we have the Gaussian surface that is inside the conductor. And to remind you, the charges are only going to reside on the surfaces. So we're going to have some Q sub A, which is the charge at the radius A, and some Q sub B, that is the charge at the radius B. Now, as a consequence of Gauss's law, because we're trying to find what the charge is inside, we can just add up the charge that is contained in there. We know that there's going to be a charge plus Q at the center. There's going to be a charge Q sub A at the surface. And those are the only places where the charge can be. So we know that the total charge inside this Gaussian surface is going to be plus Q sub A. Now, we know that the electric field is going to be 0 on the inside of the conductor. That says the left-hand side of Gauss's law is 0. And by association, the right-hand side of Gauss's law is 0, which tells us that Qin is equal to 0. And that allows us to solve for what Qa is, which says in the end that Q sub A is going to be equal to minus Q. Additionally, we can find Q sub B by saying that the total charge on the conducting shell is going to be the sum of Q sub A and Q sub B. So I could say, for instance, that this is initially uncharged if there's no charge on the surface. That says that the Q sub A plus Q sub B is equal to 0. And then if Q sub A is equal to minus Q, then Q sub B is going to be plus Q. But this total charge that I put on the surface could be, whatever I want. The shell, that is. The surface is slightly different. Okay, so the last thing we want to talk about are insulators. And so when we're talking about insulators, the primary difference between insulators and conductors is the fact that charges can move in conductors, but they can't move in insulators. And so as a result, what we need to do is we need to add up all of the charge in an insulator. And when we're adding things up, we talk about infinitesimals. And here that means that Qn is going to be equal to this scary looking triple integral of rho sub r dv. So let's first talk about what dv is going to be. So in spherical symmetry, dv is going to be equal to 4 pi r squared dr. This is like considering you have some spherical shell that has a surface area of 4 pi r squared times some infinitesimal radius that makes it a volume. Now we can talk about cylindrical symmetry. In cylindrical symmetry, similar case, we're going to say that dv is going to be the surface area of the cylinder, which is going to be the 2 pi rl times dr to make it a volume. Now let's focus more on the spherical symmetry. And the thing about the triple integral is that when we want to think about these various symmetries, we're going to assume that it's not going to vary as the angles. It's only going to vary as the radius. And so if the charge density varies as the radius, that means that we can integrate out the angles. And so that's effectively what we're doing when we're saying that dv is equal to 4 pi r squared dr. That triple integral becomes a single integral. Now, in order to think about this in more detail, let's consider an example of a spherical insulator, where this insulator is going to have a radius of r and a charge density of rho as a function of r, where rho as a function of r is the volume charge density. Previously, we talked about line charge density. This is very similar. This is going to be the charge per volume, and in principle, it can be a function. Now, let's think about drawing some Gaussian surfaces, because we'd like to find what the electric field is. So we can draw some Gaussian surface that is on the interior of this insulator, and we'd like to find what the limits of integration are. So here, we know that the charge distribution is going to start at r is equal to 0. That means the lower limit of integration, or where we're going to begin adding up these little pieces, is going to be 0. And it goes up to a radius of lowercase r, some variable radius that is inside this insulator that has a radius of capital R. So our upper limit is going to be lowercase r. Now, the next thing we can do is we can consider the Gaussian surface that is going to be outside, where this Gaussian surface has a radius of lowercase r as well. And we'd like to consider what the limits of integration are here. Now, we have to be careful because it's not going to be lowercase r. We are only adding up these charges up to where the charge distribution ends in this case. So that means that we're going to be adding these up to capital R. And so when we're writing our limits of integration for the region that is where lowercase r is greater than capital R, then our upper limit of integration is going to be capital R. And that's it for this video.